Yeah. Like you can like.
All right, so a couple things off the top. Once I get this plugged in. Overall, the exams are pretty good. The average was really high. I forget off the top of my head what it was, above an 85. So, generally you guys are pretty good. If you didn't do as well as you hoped, the next two exams, your best exams weighted more than your next best and then your worst. So if you do better on the next two exams, this would be kind of the one that's weighted the least. Right? I think the way that I have it set up on Canvas right now is I'm treating it like it's everybody's best. And that's kind of let's see. That's how I've got it weighted currently. So if I go down here, yeah, I weight it as 25%. So that's, why is this not showing up? You guys should have said something not. Hold on. Let's see if this. Anyways, once I show you that on Canvas, it's being weighted 25%. And then kind of your Connect grades, your Excel grades, kind of whatever the syllabus kind of says. My percentages jump around in the class, so I might not get it exactly correct here. If I try to do it by memory, so let's look like Connect is 10, Excel's 12.5, individual assignments 12.5, and then kind of iClicker online quizzes are 10%. So you kind of see those all being weighted accordingly. So your grades should kind of reflect where you're at, because I did get those second Excel graded as well. So if you have any questions over any type of grading, please feel free to reach out. But we should have a pretty good idea of where you're at in the class right now before we jump into the next set of materials. So any questions from me before we get started today? And sorry about for the last minute change on Monday. Hopefully you guys enjoyed my day off, right? So I think after today, I'll probably put up the next Connect assignment. Obviously won't be able to work through a whole lot of it, but just to kind of have it up there, I think it's going to help to work through those as we cover material, to kind of chip away at it. So I'll get that up early, and as soon as we kind of dive into the next Excel material, I'll get that Excel assignment up there early, even if we haven't covered every single thing yet. Okay, so those will probably be popping up here this week. Other than that, we've got this week's slides, so we'll kind of start working through those. I don't know, this stuff, so I start to get a little more interested in it. So I think we can do some more interesting things. So we talked about continuous random variables right when we left off the last exam, right? We were talking about uniformly distributed variables, that they were continuous. The probability of any one value, we said, was what from a continuous distribution? 0, right? And then in fact, all we can actually do when we're looking at these continuous distributions, which from here for like the next month, we'll be talking about the normal distribution. It kind of looks like a bell curve, so get used to seeing me draw this out, right? I might want to know what's the probability I see this random variable x take on a value in between a and b. Okay. Now, if I had the function for this line, I could integrate that function between those 2 points, get the area under the curve, and that would represent kind of the probability. So if we can know what's on the y-axis here, that would represent the probability of in between those 2 values. Now, if I integrate from the exact same point, I'm going to end up with 0. It's truly continuous. So all the same kind of stuff applies. I think I'm going to jump the gun a bunch. Some of these slides, I think it's, I'll go through them, but I think I'll kind of show you up on the board here first. So if I had that probability mass function, I could do this integration. What's lucky for us is people have already done this. So we're actually going to use their work, and we're going to use the idea of a cumulative density function. So let's say, if I were to plug in, f of a, right, it gives me the point that I'd be at on that y-axis, right? But it doesn't tell me kind of the probability of seeing something in between a and b. Right? So what we're going to do instead is, if we have a function, we can always make it cumulative. In a weird way, really what you'd be doing is, take up every small rectangle below this point, add them all up, and then plot the cumulative point. Right? So what we're going to end up doing is having this cumulative density function. And if it's cumulative, really what it's saying is, what's the probability, or actually, here, let me write this. what this cumulative function is actually saying is what's the probability that this random variable x is less than or equal to a, right? Cumulative. So start with this value, go all the way back. Just like we did in the discrete, right? If I say what's the probability it's less than or equal to 2, probability of 2 plus a probability of 1 plus a probability of 0. Well, now with a continuous variable, we don't have to necessarily stop at 0, right? We're not looking for the number of successes. This could be something like, well, income's not a good example because it can't go negative, but it could be something like the rate of return, right? So it could go off into negative infinity, it could go off into infinity. This could be a truly continuous. It's not bounded by any values. So what we could do is think about things like, well, yeah, I might want to know what's the probability that I'm below a certain value. So I would plug that value a into this cumulative density function that people have already kind of done for us. Right? What if I wanted the probability of being greater than b? How could I use that cumulative density function to find that? The cumulative density function always tells me the probability of being less than or equal to. Yeah, if I plug that value b into my cumulative density function, that gives me the probability of seeing any value less than that. Well, if I want anything above that, we're just sneaking that complement rule in there. So the reason why we went through it, I mean, it's not going to be something we even think about as the complement rule probably from here on out, because we got this nice visual, right? If the cumulative density function always gives me the area to the left, well, if I want the area to the right, it's just 1 minus that. Because we said last class, kind of with the uniform distribution, a little bit more clear now. The area under any continuous random variables curve, before our curve was a flat line, now we've actually got a shape to it. The area underneath that curve will always be 1. Because really what you'd be doing is, think about it as like the probability over these really tiny intervals, right? So you'd be getting all these really, really small rectangles, adding them all up. You just added the probability of seeing every single possible outcome for this random variable x. Okay? So area under our curve is 1. We'll use this cumulative density function idea and complement rule, things that we've talked about before. So I'm not going to waste too much time on this. You know, these cumulative density functions for really high values starts to get closer and closer to 1. That makes sense, right? If I want the probability that I see income be less than or equal to 10 million, it's going to be pretty close to 1. If I want the probability I see income less than or equal to 5,000, for those small values of that, it's going to be pretty close to 0, that cumulative density function. So we've kind of already talked about this. You know, if I want the probability being less than a certain value, plug that value in my cumulative density function. If I want the probability being greater, plug it in that cumulative density function, subtract it from 1. I already alluded to all this up here on the board a little bit. Okay. What if I want the probability of being in between two values? How can I use my cumulative density function there? We'll start using this in practice with some actual values probably on Friday. But if I think about, I've got these two values, A and B, and I want the probability I'm in between both of them. How could I use that cumulative density function?
You find the probability of like less than both of them and subtract A from B.
Yeah, right. If I found the area to the left of A, or use that cumulative density function to tell me the probability of seeing A or less, and then I use that cumulative density function to find the probability I see B or anything less. Well, what happens when I subtract this red circle area from the green circle area? I'm just left with what's in between those two values. Kind of think about it this way. If I've got the probability, and we kind of alluded to this a little bit with discrete random variables. If I have the probability of being less than or equal to 10, well, I can actually rewrite that as the probability that x is in between 5 and 10, and then plus the probability that x is less than or equal to 5. I'm just kind of rewriting that in two things. Well, then I think about, okay, if I do want the probability of being in between 5 and 10, what do I have to do? Subtract out the probability it's less than or equal to 5, which is what the cumulative density function will give me. And so that's why that kind of procedure works, right? It's almost like you could break down the probability of being less than B into these two areas. If I subtract out this area, I'll be left with the one that I wanted, which is just that being in between those two values. Any questions on that? It's gonna be too bad yet. oh, I don't know, this is, if I wanted the probability being less than A or greater than B, well, one thing that gets kind of nice is we don't have to worry about intersections or unions as much when we're dealing with these continuous random variables, right? I can't see any X value that's greater than B that would also be less than A. It's just not possible. And so we don't have to worry as much about these intersections. We have a lot of mutually exclusive events. So if I wanted the probability of being in either one of those ranges, well, I could still just find the probability of being in between A and B, subtract it from 1, and I know that I'd be left with just what's in the tails here, right? Because the area of that entire curve is 1. So if I can find the probability of being in between A and B, the probability of being less than A or greater than B would just be 1 minus that. So we're really going to start to find these probabilities of being below certain values and then have to use those. And I think having the visual always makes it a little bit easier, kind of maybe doing a little subtraction, a little bit of extra work to find the area that we want, right? Or the probability that we want, probability of being in between certain values. And this will take a little bit more, and once this actually takes some form, it'll make a little bit more sense. But I'm kind of leading us into thinking about this system more generally, and then we'll talk specifically here about the normal distribution. So there was this really smart guy back in the day, kind of jack of all trades as people were back then, who discovered what is called the normal distribution, sometimes called the bell curve, or also the Gaussian distribution, right? Taking his name. Okay? So it's pretty influential. I guess an anecdote just to be fun today about this guy. Supposedly, when he was a kid, this is like some old legend, right? But he was misbehaving. The teacher told him to go stand in the corner, add all the numbers up from 1 to 100. Right? Thinking, oh, this kid's in grade school, it's going to take him forever, right? 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5, all the way up to 100. Right? Comes back in a matter of seconds and has the answer. So, how could you very quickly add up all the numbers from 1 to 100? Start thinking about it. What's 1 plus 100? 101. 2 plus 99. 101. 3 plus 98. 101. You would have that all the way down to you get to 50, 51, which add up to 101. So you'd have 50 pairs that add up to 101. Maybe scratch some multiplication down in front of you. You can tell you that's 5,050, right? Maybe. There we go. Right. So this guy was really smart. He could see this as a kid, kind of these extremely difficult to think about formulas. In fact, you want to add up two numbers starting in 1, you want to add that up to whatever number n you're interested in. It actually follows a functional form. Right? And it's this idea that you can kind of take that all these pairs will add up to a certain value, and it's just a matter of how many pairs you have. So anyways, really smart, comes up with this normal distribution that pops up everywhere. Okay? So I think a couple of examples, so human height, rainfall, and then eventually we can apply this normal distribution to linear regression, which allows us to make some really influential kind of predictions. I put human height and rainfall here. It's really interesting. So like any biological marker almost naturally follows a normal distribution. So I've got a couple, I think, examples of other variables here today we'll look at, but human height, human weight, anything that occurs, temperature, rainfall, naturally, generally follows a normal distribution. It's kind of weird that pops up this often. So if we have this normal distribution, I'm telling you it's a bell curve. I've kind of already drawn it out here a couple times to kind of look like this pretty symmetrical curve. So you should know that I'm not perfect at drawing this, right? But should be symmetrical, right? So there's no skew to a normal distribution. Its mean is equal to its median. However, how high that distribution is, or kind of how flat it is, will depend on some things. And then where is it at along our x-axis will also depend on a couple of things. But if I wanted to graph out that line, the equation that I would need, right? This has some equation that's kind of allowing me to graph that normal distribution line. It's going to look something like this. So this is pretty nasty. We're not going to use this. Well, we are, but it's going to be behind the scenes. Right? So don't write this down. In practice, this is the formula that I would be integrating. So you can imagine how fun that would be, right? Integrating this function in respect to x, right? The thing that we're choosing, not very fun. But what's kind of interesting just to point out about it, it does pop up in nature. I don't know, you can go down like YouTube rabbit holes of the golden ratio and all these things. But notice we got these two really unique numbers, pi, and then that natural number e, that both happen to be in this normal distribution probability mass function. Right? So it's these really weird numbers that we're not really sure exactly, you know, why they show up so often in nature, so often in these mathematical formulas, and they both happen to be in this normal distribution function. And then the normal distribution ends up being very helpful in terms of mathematics down the road. But if we look at the rest of this function, right? So x is just these different values we'd be plugging in to that function, right? A, b, whatever they happen to be. Other than pi and e here, the only other thing that's really in this formula is our variance and our mean. So these are the two things that are going to define our normal distribution. So, for example, human height and rainfall both follow a normal distribution. But if I'm thinking about, they're both measured in inches, right? So if I'm thinking about, I'm going to put them on the same graph, because why not? I'm going to put both distributions on there. They're both having the same units. So I'll think first, I don't know, what's the average rainfall? I don't know, it's something like, let's say, I don't know, 3.5 inches, right? So any given month, on average, you get about 3.5 inches of rain, but every month it varies a little bit, right? Sometimes you'll see a little bit higher rainfall, other times you'll see lower rainfall. Now, what are the most likely outcomes, or where do we see this probability distribution be highest, right? You can almost think about this like the discrete, like where are the highest bars? It's just now it's continuous. It's this nice line. Well, the highest points are values really close to that mean. But if I then want to graph human height, it's also in inches, but where is that going to be? The average for human height, I think it's something like 68, and actually it might be males. I think the overall is maybe like 65 if we look at kind of across gender there. So we still have a normal distribution. Height still follows a normal distribution. It's just that mean will shift where it's at. Okay. In terms of what does the variance do? Kind of hold off on that discussion for a little bit. We'll kind of build up a little bit more about this normal distribution and then think about, okay, the mean will shift our distribution along the x-axis. The variance will do something else to it. Okay? So a little foreshadowing there. We'll kind of come back to that. So some characteristics, right? I already mentioned it's symmetric. So it should fold like on top of itself and kind of look at the middle point of it. The mean will be equal to the median, which is equal to the mode. I already mentioned the mean and the variance will define it. So this is just things I've already mentioned here. It's not like a quiz you necessarily on these, but these will be things that we can start to look at. So I already kind of showed you, you know, and I tried to give you an example of like two things that had the same unit, right? Inches of rainfall and inches of height. So we could just put those on the same graph, but that difference in mean is going to shift my distribution. Okay. If I then think about the variance, try to give you a little bit more insight as to what that's going to do. So let's think about, I've got some distribution. We'll call this kind of the first distribution. And I don't know, its variance is 10. Right? So we kind of already alluded to, you can think about this distribution telling you that values that are really far from the mean, not as likely for us to see those. And that makes sense. Remember when we talked about the discrete random variable, whatever the mean of the expected value was, was the most likely outcome. And then as we move from that point, the probabilities decline. Well, notice that same thing is true for the normal distribution, right? As we move away from that expected point or that mean, the probabilities decline. So values that are pretty close to the mean here have a pretty high likelihood of occurring. Right? You can think about, you know, I don't know. Like I said, this is think about human height, right? It's about think about no. I think 5'4" is female and 5'9" is male. So what, like about 66 inches there, right? would be the average human height. So the probability that I select somebody at random, what's the probability their height is in between, I don't know, 62 and 7? Well, pretty likely, right? What's the probability someone's in between 5'2" and 6 foot? That's the bulk of people, right? That's the majority of people. Pretty high probability of seeing those values. But what's the probability that I see them be, I don't know, greater than, oh, what's a good value? We'll do, what's 72? No, not 72. I want 84. So probably they're over 7 feet tall, right? Pretty low, right? That value is very far from that mean. Okay? So that's kind of the idea behind what we're doing. So we then think about, all right, maybe I've got this other distribution. So maybe this was human height in America. I then go over and I look at some Scandinavian country, and I don't know, maybe they have a similar average, right? But the variance is much higher. Okay. So I know that the variance in this second group is much, much higher. So if the variance is higher, what does that tell me if I was looking at data? That the values are more spread out. So a higher variance is going to spread out our distribution. But what does that really mean visually, or how can we kind of connect that? We'll also think about what a higher variance is telling you is that values very far from the mean. If I have a higher variance, those values should be more or less likely. If I have a higher variance, yeah, that means values further from the mean are happening more often, right? Now we have probabilities here, but remember, probabilities are generally, if the way we empirically assign them, from data. So you can think about this as we see these values happen more often and more frequent, right? The variance is higher, we're going to see these extreme values more often or at higher probabilities. So you can kind of think about values very far from the mean. Those probabilities are going to be a little bit higher. But remember, the area under the entire curve still has to be 1. So if these values have become more likely, those values further from the mean, what has to be true about values that are closer to the mean? If the area under the curve is 1, and I now know that there's a higher area there in the tails, what has to be true about these values near the mean? They're less likely, right? I mean, you know, these have to add up to 1. So if something gains something, it's a zero-sum game. If one of them gains probability, something else has to lose it. So with a higher variance, what we actually end up with is that values close to the mean become less likely, values further from the mean become more likely, and we get kind of this flatter distribution. All right. Now, it's easier, I think, to think about, like, as the variance gets higher and higher, our distribution is more spread out. But what does spread out mean? Spread out actually means we're kind of getting this flatter distribution. The tails, the values further from the mean, are getting more likely. The values really close to that mean becoming less likely. So you can think about it, we plug in these different values, right? As my variance starts to get higher, I start to get this flatter and flatter distribution, where the values and the tails become more likely, values in the mean become less likely. Any questions on this before we keep moving? Is this making sense so far? A little bit. All right. So if I think about here, we put like male and female height data, we can kind of see a combination of these two things. So male height tends to be a little bit higher on average, right? So that would kind of shift our distribution to the right. But male height also tends to be much more variable, right? I mean, I guess the idea I would give there is there's a lot more men even over 6'6" than there are women, right? Like significantly. It's just a wider distribution. It also means that if it has a lot higher variance, not only is that right side kind of go out further, but so does the left side, right? So we tend to see kind of shorter than average males more often than females as well. So we've got a shift in the distribution because the mean is different, and then because that variance is higher, it flattens out that male distribution of height, right? So kind of visually, it looks shorter, right? It's more spread out, it's flatter. questions on that. But this is like actual data that they collected. I mean, they smoothed it out a little bit. We'll look at a couple kind of later, but yeah, if you look at male height and you look at female height, they are both almost following exact normal distribution. Excuse me. So then what we're going to start doing, and you don't have to memorize this number. I'm just showing it to you for right now. But there's going to be a process for which we can prove this to be true. So I don't think we'll probably get there today. Friday, I'll definitely prove to you this is the case. I'll kind of revisit this idea. But the idea is here, if I ever, it doesn't matter what that mean is. If I go 1 standard deviation above and 1 standard deviation below, right? Those in practice will be some value, right? I can calculate the mean of a variable. I can calculate the standard deviation. I can then figure out what value would represent being 1 standard deviation away from the mean and 1 standard deviation below the mean, right? So if you want to use the human height example, you know, I don't know, maybe the standard deviation is 5, right? So if the mean is 66, the probability that if I choose a person at random, they're somewhere in between what, 71 and 61 inches, 1 standard deviation above and 1 standard deviation below the mean, that probability will always be 68 point something, 3%. Right? So it doesn't matter what the mean, it doesn't matter if you're looking at human height, it doesn't matter if you're looking at rainfall, you could be looking at temperatures, you could be looking at age distributions, even years of age. If it follows a normal distribution, there's a 68% chance that if you select 1 person, in my examples at random, or 1 month at random, thinking about rainfall, that you'll see that continuous random variable that's normally distributed, probably it's in between 1 standard deviation above and below will always be 68%. So like I said, hopefully we can prove that kind of by Friday. But that is just a general fact, right? So it's pretty high, right? I mean, being within 1 standard deviation of the mean, it's more likely than not, right? It's above 50%. What if we go to 2 standard deviations? This is where it rapidly increases. Kind of notice, you know, I try to draw this, but like I get a more gradual decline and then a sharper decline as I move further and further from that mean. So once I go 2 standard deviations above and below that mean, the probability that if I selected a person at random, their height is somewhere in between 2 standard deviations above or below the mean, rises all the way up to 95% or 95.4%. And then I can keep going, right? 3, it's like 99.7. I could go out as far as I want. So if I'm up at 2 and 3, at 3 standard deviations, I'm already at 0.997. So what happens, do you think, if I went out 6 standard deviations on either side? That probability is going to be really close to, it's basically 1. Which, I don't know if what classes some of you have had or what. Everyone's got different majors. So, have you heard of 6 sigma yet? Or have you heard this mentioned? This is essentially where it comes from, right? If I can if I can go 6 sigma, 6 standard deviations above and below, I can almost guarantee that I'm going to see the value somewhere in that range. So I don't have to worry about these extremely high or low values. If I go out 6 standard deviations, I can almost guarantee you that whatever the unexpected or the future event is I'm looking at, the value is going to be somewhere in that range. That's kind of, I mean, I'm simplifying a little bit, but that's kind of the idea behind where 6 sigma comes from. All right. So we'll revisit those numbers next class. Hopefully we'll have the tools by then to kind of prove why that's the case. But I'm just telling you. So we've got a normally distributed variable. The way that we'll write this is this variable x is normally distributed with this mean and this variance. In practice, the mean and the variance will be given to us, right? Or we can calculate it from data. So we've got this mean and this variance. And then you can think about it, if I went all the way back to that probability mass function, well, if you tell me the mean is 50 and the variance is 20, I can plug those values into that function and start to integrate over certain values to find the probability of being in between certain values. But we don't want to do the integration. Right? So we're going to kind of try to sidestep this. And in order to do that, we need to get a normally distributed variable into what we call a standard normally distributed variable. So a standard normally distributed variable will have a mean of 0 and a variance of 1. Oops, sorry. So a standard normally distributed variable will have a mean of 0 and a variance of 1, or the variance is 1. For the standard normal distribution, what's the standard deviation? Just the square root of that. The square root of 1 is 1. So the standard normal distribution has this nice property that the variance and the standard deviation are exactly the same. Okay. And we can exploit that a little bit. So I think I'm jumping the gun a little bit here, but I think based off what I said, it's a good time to introduce this idea. So let's say I've got a standard normally distributed variable. Okay. For now, I'm going to call that variable z. There's a reason why, but that's the notation we'll end up using. But for now, instead of x, we're thinking about a variable z that's standard normally distributed. So z is normally distributed with a mean of 0 and a variance of 1, or standard deviation of 1 as well. So if I think about this variable, and I were to go out 1 standard deviation above the mean, why might that be helpful when I have a standard normally distributed variable? Well, if the mean is 0, then when I go 1 standard deviation away, that value would just be 1. So if I can get a standard normally distributed variable, whatever value that variable is, it's really just telling me the number of standard deviations away from the mean that I am. So let's say I had something that was 2.5 standard deviations above the mean. Well, if the standard deviation is 1, then that z value would just be 2.5, right? Because if the mean is 0, standard deviation is 1. If I'm 2.5 standard deviations, 1 times 2.5 is 2.5. So these standard normally distributed variables, we like them because whatever the value is, it's already telling us this is how many standard deviations away from the mean that you are. If I have just a regular normally distributed variable, and you tell me, well, the average rainfall is 5 inches, standard deviation is 1.359. Okay, the rainfall this month was 5.73. How many standard deviations away from the mean are you? I don't have any idea. All right, I'm gonna have to bust out a calculator. I can't do that easily in my head. But if I've got a standard normally distributed variable, the value of the variable just tells me how many standard deviations away from the mean I am. Right? So we want to turn these normally distributed variables into a standard normal distribution, or transform them into a standard normal distribution. So we're going to call these z values. There we go. And really, if I have a standard normally distributed variable, we'll kind of write those in z, just kind of help tell the difference between a normally distributed variable and a standard normally distributed variable. But they're really nice because a z value of 1, we have 1 standard deviation above the mean. Z value of -2, I'm 2 standard deviations below the mean. So we want to be able to get these z values because the interpretation becomes a lot easier. Okay. Any questions? We're keep moving here. I know a lot of conceptual stuff today. We're kind of building this up. Okay. So why don't we transform a normally distributed variable into a standard normally distributed, standard normally distributed variable? We're going to call those new values z-scores, right? So the way that we're going to do this is we're going to take this original variable x, whatever values that we're interested in. So maybe this is like 15. I'm interested in what's the probability I see rainfall below 15 inches. But we're going to have to convert that original variable of rainfall that is normally distributed into a standard normally distributed. How do we do that? We will subtract the mean of the variable we're looking at, and we'll divide by the standard deviation. So I'll try to give you a little bit of insight as to why this works. I'm going to try to leave this up here. So let's say this is my variable. It's symmetric. We'll assume that just a very easy toy example, but it is a normal distribution. Okay? Values that are equally, on either side of it. So if I calculate the mean here, and do what? Add these all up and divide by 5. So what? 10, 10, 10, 30 divided by 5. should get a mean of 6. Okay. Well, what's my standard deviation? Or I guess we can kind of think about what's my variance. Well, I could go through each one of these. So I'd have to subtract the mean, square it, right? Add them all up and then divide by, I'm treating this like a population, just the number of observations I have. So I'll try to do this down here. All right, if I take like, so we'll do this. So what, 2 minus 6 is what? -4 squared is 16. 4 minus 6 is -2, squared is 4. 6 minus 6 is 0. These end up being nice because they were just equally as far away from that mean. So I add these all up, I get what? 20 plus 20, so 40 divided by 5. Doing the math, my height correctly. Why does that not look good? 16 and 4. No, that's right. Okay. So I've got my variance here of 8. So what would my standard deviation be? Just the square root of that. Okay. So if I then want to create a standard normally distributed variable z, what's that first x value's z score, or what would it be when I turn it into one of this z value, or this standard normally distributed variable? I take that value 2. I subtract the mean of 6. So I got what? -4 there. And then divide by that standard deviation. Everybody with me so far? I then go to the next one. 4 minus 6, -2, divided by the standard deviation. Go to the next value. That one's easy, which is 0. Go to the next one. 8 minus 6, 2, divided by that standard deviation. And then the very last one. Okay. So if I start out with a normally distributed variable, and all I've simply done here is I've subtracted the mean and I've divided by the standard deviation. Well, notice what are these? If I try to find the mean of this new variable, what's it going to be? If I add these values up and divide by the number of values I have, what do I get? What happens here? I add -4 over square root of 8 to 4 over the square root of 8. That is 0. 2 over square root of 8 plus -2, 0. Plus these add up to 0. Doesn't matter that I'm dividing by 5 because I've subtracted the mean. When we subtract the mean from all these original x values, our new variable will be centered at 0. Right? So that's why we subtract the mean, because it centers that new distribution at 0, which is what we want. We need a standard normally distributed variable. If I were to go through, I could kind of think about creating this other column. Well, if my new mean is 0, it becomes pretty easy to find the difference between this z value and the mean of z, because the mean of z will always just be 0, right? So -4 over the square root of 8 minus 0. Well, I could just think about that as that's 4 over the square root of 8 squared. So what does that become? 16 over 8 or 2. 2 over the square root of 8 minus 0. Well, it's just -2 over the square root of 8 squared. 4 over 8 or 1/2. 0 minus 0 is 0. And then kind of the same idea here. 2 over the square root of 8 minus 0 is just 2 over the square root of 8 squared. And then down here, we have the exact same thing. Okay. So now I'm thinking about, I'm not done, I haven't found my variance, or I haven't found my standard deviation yet. I need to then add all these up, right? So what did these add up to? 2 plus 2 plus 1/2 plus 1/2 is 5. I still need to divide by the number of numbers I have, which is 5. Lo and behold, my variance or my standard deviation will be 1. Right? So by subtracting that mean, we centered the new variable at 0, and when we divide by that standard deviation, that's what allows us to always get that the new variance of this variable z will be equal to 1. And you can, I mean, if you choose values that are normally distributed, so you'd have to have an example like this where they're symmetric, but you could write down the values. Let me think, 1 to 100. And you could go through all this, or you could prove this to yourself in Excel that it works out that if you subtract the mean, divide by the standard deviation, you always end up kind of with this this new standard normal distributed variable that has a mean of 0, variance of 1. Okay. Any questions? I didn't have to do all this either. You're not gonna have to do this every single time. I just wanted to kind of give some of an insight as to why these z-scores do follow this standard normal distribution. Which, if they do, now they become really useful, because now if I can convert an x value, right, some human height or some inches of rainfall into a z value, that z value tells me how many standard deviations away that value was from the mean. So if I get a z-score of 0, that means that the value was the mean, right? It's 0 standard deviations away from the mean. If I get a z-score of 3, that means whatever x value I convert into the z-score must have been 3 standard deviations away from the mean. And then the sign there, just to kind of mention, right, if they're negative, that tells us that it's a certain number of standard deviations below the mean. All right, so I like this photo. Stole another one from the book. But I want to kind of show where this comes from. Hopefully everybody had this written down. Not that you necessarily have to go back to that, but so another thing I like to think about is, let's say we started out with something like this, right? So we've got some normally distributed variable x, and I'm just thinking about 2 values, being 1 and then being 2.5 standard deviations above that mean. So if I want to turn these into z-scores, and I know that the z-score equation is take the x value, subtract the mean, divide by my standard deviation. So if I want to find the z-score here, notice this x value is the standard deviation, sorry, the mean plus 1 standard deviation. I'll then subtract the mean, divide by that standard deviation. This cancels, these cancel, this is just 1. Right? Well, what if I want to find the z-score for a value that's 2 standard deviations above the mean? Well, it's 2.5 standard deviations above the mean. That's the x value that I'm looking at. I subtract the mean, divide by the standard deviation. The means cancel, this cancels, and I'm left with that z-score of 2.5. So we can easily map, like once we actually have the mean and we have the standard deviation, we can map different values down to what their z-score would be. So in practice, this mean might be 53 and the standard deviation might be 4.5. So these are going to be a little bit more difficult, right, numbers to look at. But as long as we have that mean, as long as we have that standard deviation, and we're converting these to z-scores, should be these z-scores just tell us the number of standard deviations away these different x values were from that mean. And then notice what happens if I want to find the z-score of the mean. Now my x value is just the mean. The mean minus the mean is always a z-score of 0. Okay. So one nice thing is that for our standard normal distribution, that mean of 0 exactly splits our distribution in half. So what's the probability I see something above or below the mean from a normal distribution? Area under the curve is 1, right? So that value of 0 exactly splits that in half. The probability I see something above the mean of 0 is 0.5. The probability I see something below the mean is 0.5, and that's partially because it's symmetric. So the mean is the same as the median. So we always know there will be 50% probability of seeing something above or below that mean. So what are we going to do with these z-scores? Right? What's the point of it? Right? So once we have this z value, or how many standard deviations away a certain value is from the mean, we can then plug it into a cumulative density function where someone's already done all this integration for us. They've integrated that probability mass function that was nasty from negative infinity up to whatever value that we tell it. right? So we're always going to be having the cumulative probability or the area to the left of whatever value we're plugging in, or in this case, we're using z value, so whatever z value that we're plugging in. So the setup might be we still start out with a normally distributed variable x, and we want to know what's the probability that we're in between two values a and b. So what we can do, oops, let's skip ahead here, is I'll put this up on Canvas before next class. And I would suggest probably printing this out when we do some iClicker stuff in class, when we start working through problems in class. It's easier to have this in front of you. Even if I try to show it to you, it's really small. So print it out, or make sure you have a device you can pull that up from Canvas, a PDF that I'll put up there later this afternoon. We really kind of need this moving forward. Okay? But the idea is, let's say, I have some value, I turn it in some value for x, I turn it into a z value, and I find that its z value is negative 1.29. So whatever value I was starting out with, it was 1.29 standard deviations below the mean. I'm then maybe interested in, okay, so what's the probability that I saw that original value for x? So maybe this was like human height. I don't know, maybe we saw 63, someone be 63 inches. Well, what's the probability that they were 63 inches or anything below that? Well, I first have to turn that into a z-score. I did. So I got negative 1.29. And now I just want to plug that value of negative 1.29 into that cumulative density function. And that cumulative density function should spit out at me the probability that I see this value or anything lower, right? Or anything to the left. So how do I find that probability? How do I know that it's 0.0985? Well, I've got this table, right? So the way that we read this table, this is basically someone has integrated that probability mass function for every value of z out to the second decimal. So the first column is kind of our first decimal, right? So negative 0.1, negative 1.6. This column headings, right? Those are going to be our second decimal, the hundredths place. So for instance, negative 3.51. The probability I saw something that many standard deviations below the mean, or anything below that, right? Anything to the left, that probably is only 0.002. And then if I go, okay, what if I was 2.55 standard deviations below? So negative 2.5, go over to the 5 column, the probability I saw something 2.55 standard deviations below or anything less is 0.0054. Well, I get the negative 1.53. Probably I see negative 1.53 or anything below it is 0.0630. So the value we had is negative 1.29. So negative 1.2. The second decimal of 9 is all the way over here. All right, so the probability I see that z value of negative 1.29 or anything below it is that value where those mean. Okay. So I first have to look up the first decimal, then I look at the second decimal, and where those meet, that number represents the probability I saw that z-score. Sorry, I forgot my 1 here. This was negative 1.29, right? The probability that I saw that z-score or anything below it. So every number in this table in the middle essentially is kind of giving you an area to the left, right? It's not a very technical way to call it, but that's what it's visually representing, right? The probability of seeing that z value or anything to the left of it or anything below it. Okay. So for all these negative z values, what should the probability always be of seeing that z value or anything below it? For every negative z value, probability I see that value or anything below it should be less than. What's the probability that I'm less than 0? Since 0 is the mean, so the probability I'm less than the mean is 0.5, right? So I know this area is 0.5. Even if I just went to like negative 0.001, I know that the new area to the left is going to have to be just slightly below 0.5. So sure enough, if I look at all these probability values in the middle, what's true about all of them, they're all below 0.5. In fact, not until I get to negative 0.00, okay, now the probability is 0.5. Okay. And what do you think is probably true for every probability I would look up for a positive z-value? If it's the entire area to the left, for every positive z-value, those have to be greater than 0.5, right? They will include this area plus a little bit more, right? So I think I've got that one up here, right? You can look at something that's positive. You'll notice here all these probabilities are above 0.5. Okay? So we'll use both kind of sides of this table. So they'll have two sides if you're printing it out and you want to bring it. It should have a front and a back. I'll kind of expect that you are able to pull it up in front of you or have a physical copy of it from here on out. Other than that, we're going to finish up or kind of, I guess, continue down the standard normal distribution, how we use this table, and actually have some problems where we come up with some pretty interesting probabilities for. Okay? Yes, you can keep your exams. Yep.